So let us continue. So we were in the chapter linear predictor. So I guess it's chapter 9. And in linear predictor, our goal was to construct a predictor which is linear, okay, to classify two different classes. So let us say this is one of the class and this is another class. Okay, these are the given data that is given to us. So a realistic application could be, let us say you want to classify spam email with non-spam emails. Okay, spam emails and non-spam emails. And when you are building a classifier for spam, non-spam email, then these data points might correspond to the keywords that you may have seen in the spam email and the keywords that you see in the non-spam email. Okay, so the data points will represent certain features in your email. Okay, so these will be so this will be the way you model the data, how you extract the features from your data. So based on this, then your goal will be to build a classifier that can classify these two. So basically the idea is to learn a linear predictor. In this case, we call it linear because we are only looking for the linear predictor here. Linear, let's say in this case, a line, or in a higher dimensional space, it will be some plane. Okay. So this is the problem we are studying. This is one of the basic problems in machine learning you encounter, where you are looking for linear predictor. And we have seen in the last class that not all set of classes are linearly separable, right? Because you can also have data sets like this, and then the other class is like this. Okay, so certainly you cannot have a plane that can separate these. Okay, so such data points are not linearly separable. So we are not considering these cases for the moment. We are only looking into cases which are linearly separable. Okay, in this case you may learn a separable. You can learn these data by allowing non-linear separators. So maybe in this case you will learn something like this. Okay, so this circle is a non-linear function, right? So in this case, in future, if some data comes here, then you will say that it's inside the circle, so it should be one class, and if it's outside the circle, then it's another class. So we started with this, the most basic case, and then we said that one of the things, the results that we know is a separating hyperplane theorem, and then we said that if I indeed make a convex hull of these and they don't intersect, then certainly there is a guarantee that there will be a linear separation. Okay, in this case, as you can see, the separating hyperplane doesn't work because they don't remain. So if in this case, if I construct a convex hull, then this will be this, and convex hull of these points will be this. So they don't, I mean they intersect. Okay, they are not disjoint. So in that case, I cannot build a linear separator. Okay, so these are the things we have seen, and since we are looking into linear separator, linear functions are naturally defined by planes. Okay, so in this case it's a line, but obviously the data points are in the 3D space, and here then I'm looking for some hyperplane. Okay, so most general linear classifier will be some hyperplane. Okay, so and we know that the formula for a plane is like this. Okay, so this is the plane. Okay, this is what we know from vector calculus geometry. This is how planes are written with normal in W. Okay, so essentially what we are looking for is a a plane W transpose X plus B. Okay. So if I allow this plane to be very floating type, right? Because initially I don't know, right? So initially I don't know what is a suitable W, okay, and B. Okay, in this case B is also unknown here. So plane is defined by knowing B and W. Okay, and we did a trick in the last class that we can kind of observe B in W as well by just doing a little bit of a padding. Okay, so in this case I can change my X vector tilde to be X and then appended by 1. Okay, so then it becomes a new, you can say X, okay, just 1, and then W tilde we append this by W comma B. Okay, now the plane equation can be written as, let us say Px is W tilde transpose X tilde, right? So if with this W tilde I multiply X tilde, okay, if I take a dot product, I exactly get this W tilde X times B dot 1. Okay, so we can kind of see plane also like this in a compact form with this small change in the notation. Okay, so essentially what we are trying to say is that B is also an unknown that needs to be found for a plane. Okay, so then the learning problem is about finding this, obviously about finding this this plane, but then this plane itself has to tell us, give us some pointers on which data is where. Okay, so then we said that that we need some way to tell which is which side. Okay, so then we said that okay, if these data points of one class remain on based on the angle, if they make a acute angle, then based on the angle which cos theta of that, that if it remains positive, then we will say that okay, it's on this side of the plane, and then based on this data, if they, because since W is fixed, once a plane is run, W will be either this side or this side. So let's say this side without loss of generality, then these data points all will make acute angle with W, meaning sine of W transpose B. Okay, that's exactly what cosine will mean, right? So what we know from, I mean not W transpose B but the X. Okay, and what we know is that W transpose X is norm of W, norm of X, cosine of the angle between angle between W and X. Okay, this is what we know from geometry, right? So essentially what essentially means is that these guys are positive anyway. Okay, so these guys are positive because these are norms. So essentially what you are saying is that cosine of the angle that I'm looking for is exactly determined by the sine of W transpose X. Okay, so cos will be negative and positive based on W transpose being, cos will be, the angle will be acute or obtuse based on the sign that W transpose X is making. In other words, the points will be on this side or that side depending on the sign of W transpose X. Okay, so that's what we need as an additional step, that we will have the sign of the W transpose X. Okay, and then based on that we will learn the classification of these. Okay, now in the supervised learning these data is already told to you. So in this case it's told that let us define this as to be the positive class. So all these are positive class and these are negative class. Okay, so this is a tag that we give, positive class, negative class. In this case it matches with the sign also. Okay, so it makes sense to say it's positive and negative class. So then we say that so then it's a supervised learning problem. So So what it means is that W can be learned based on the supervised data, that these X are known, these classes are known to be positive, these classes are known to be negative. So based on that, I can learn a W. Okay, so that's what the learning process would mean. So we have formulated this exactly in the last class. So basically, we can build a loss function now. Okay, so the loss function will tell us that each time the way we have to do is that we have to calculate the sign, and so sign of, let us use this notation. Let's say sign of W transpose W tilde X this, and each time I will check with the, for the given X. Okay, so let us say this is Xi. So now I'm looking at this guy, let us say X, this sample which is Xi. So this Xi sample came, and with the current W that I have, because W is something I have to learn. Okay, so W is a variable right now. X is known for us because X is the supervised data. So for this, I will check. Okay, let us say the check is done with, let's say, minus. Okay, minus of whatever yi, which was supposed to be for Xi. Okay, so this becomes my loss, let us say, for the ith sample. Okay, so I'm not very precise here right now. I'm just reviewing what we have done. We have actually done this already. So just to give you another view, summary of what we did. So what is happening here is that this is the loss we built. We are saying that, okay, I go for each sample Xi, and I check for what I really want is W transpose X for that Xi must match with the corresponding yi. In this case, Xi is on this side. So what I am looking for is the sign of the angle, I mean the angle that Xi makes with the current W tilde must match with yi. But obviously, when you start an algorithm, because it's an iterative method, your initial W tilde that you will start with, because it's iterative algorithm, so you will choose something random initially, because you yourself don't know, because that's the problem in itself, right? To find this optimal W is the given problem itself. So so what essentially all this is a minimization problem over sum of Li. Okay, so we can write like this. Okay, so basically we are supposed to minimize this for a good choice of W tilde, for which the sum of the losses on all the samples, all the samples is minimized. Okay, so we have done this formally in the last class. And so all this, what it means is that initially what will happen is that, since you will use a gradient descent to minimize this, initially you will choose W which will be very random. So initially your W, your plane will be like this. Okay, and it will, since your plane is like this, your loss will make a lot of errors, because it's misclassifying these guys as positive. Okay, because your W tilde is now pointing this way. So certainly it's making a lot of high loss. So this as a function of W is high. So then gradient descent will come in picture, and then gradient descent will tell us that, okay, we are supposed to minimize this. So what is the possible direction of W for which my function will decrease? So the calculus tells us that go in the negative of the gradient at W tilde direction. Okay, so this is my W tilde 1. Let's say I started with this, which is making bad error. This is the loss function that's making high error because it's bad. Okay, and gradient descent is telling me, okay, I'm to minimize the loss. Let us go in the direction negative gradient of the gradient of the capital L, let us say, which is the capital L is the sum of these Li's. Okay, so the whole loss over all sample. So let us go in negative L W direction. Okay, so that's what gradient descent tells us. As a function of W, if I have to minimize a function, then I have to go in the negative gradient direction. So that's what it will do. It will go in the negative gradient direction, and with that a new W tilde will be created, which will be old W tilde minus gradient W tilde L W. So if I have to be precise, then it's I plus 1 at the ith step. This is the ith step, ith step. Okay. So this is what gradient descent. This is how gradient descent helps you. Okay, initially, then it will improve a little bit. Okay, because it has minimized. So certainly it has corrected itself a little bit. So next time it would be like this. So this will be w tilde 1. So this is 2. Still it's making error. So here it's misclassifying this guy. So again with that w tilde 2, now you will again calculate the loss. Loss is high, so gradient descent will again tell you to update further and go to w tilde 2, and then it will improve again. So at some point then it will make no loss, okay, because it's classifying everything, because everything is based on the supervised data, because your whole loss is based on the supervised data. So there will be a point where, if it's linearly classifiable, there will be a point where it will make no error. Okay, so once it makes no error, basically it has no improvement to be done, so you can stop your algorithm. Basically in that case, gradient should become flat, because this loss should go to a minima, and in that case the gradient must be 0. So in that case, in your algorithm you can check the norm of the L, and then you know when to stop. So when you stop, then you know that classification has happened. And then so let us say while doing this, you arrive at the optimal W, which we call it W star, which is the final, let us say you have learned a plane like this. Okay, so once I have learned a W star, this was the learning process. Okay, I have learned it. Now the next time, so while learning it was a function of W, and X was known. But once I have learned, now it's W is known. Now I make it a function of X. Okay, and obviously, like, since I have doing a prediction and so on, so I will make it a sine of W tilde X, W star X. So this becomes my prediction problem, prediction function, right? So now for a new X, okay, if you give us new X, let us say some new X came and it's somewhere here. Okay, so let us say we call it xt, the test data, and you put that xt here, you check for the sign, and if its sign is positive, then you say that okay, it's the positive class. If sign is negative, then you call it a negative class. Okay, so this is a review of the linear predictor and how gradient descent helps you in this. Essentially, whole of machine learning is an extension of this idea. Okay, it's just that the simple linear predictor is now changed to something very complicated later on. Okay, for example, neural networks. Okay, so essentially all this can be extended. The whole of machine learning is all about this. Okay, so then so we have done this in the last class. We have built a perceptron model as well, and we have proved that the algorithm will converge and so on. So we have done these proofs, and then so this was for classification, and then we have linear regression problem. So essentially, machine learning problems classify into two types. Either it's a classification problem or is a regression problem. Okay, so classification problem is when you try to classify set of data. Okay, so spam email, not spam email. Okay, so this is a classification problem. And another type of problem we have already seen in some sense. It's a fitting problem. So that's called regression problem. So where I'm given set of data and I'm telling what is the best curve that passes through that data. Okay, so this is classification problem, and fitting is called a regression problem. Okay, so in linear regression, maybe we are looking for a linear function that fits through this. Okay, so so in the linear regression case, we are still looking for these linear functions, which are, let us say, x goes to, which are still planes. Okay, plus b, and then w in rd and b in r. So in the regression also we are saying that right now I want to focus on just planes that the best plane that fits the given data. Okay. Now this problem is a little bit different from this. Okay. Here I may not be able to go through all the data points exactly because it's about passing through the data points exactly, but which may not be possible in this case. So in this case we have to look into the errors that we make like this, how far the error we had, and take collection of these errors and then build a loss function and then minimize the loss function here. So in this case the loss function can be h xy, which is hx minus y whole squared. So this is the typical L2 loss function that we use for the regression problem. So these are your y data, and this is the hx is the prediction on that. Okay, so these are our x, and these are the corresponding y. So it could be x1. Our prediction is hx1, and the actual data was y1 and so on. So we can build a generic loss function here where we will sum over these. So xi minus yi whole squared I equal 1 to m, 1 by m. So once again we can build a loss function which takes the difference between these. So as I said, here we could have built a loss function based on the count itself. So how many times I did a good prediction. Okay, so it may be based on the count itself. Okay, so how many points I classified correctly, how many points I didn't classify correctly. So a correct way to do this would be based on the count. Here it's based on the difference. So hx1, how far it's from y1 and so on. Okay, so we have added all these loss functions here, and now we have this, and then the idea is similar now. We try to minimize this loss function for the various for the given data x, and the unknown that we have is the w, which is the weight vector here, and it's an optimization problem. So when we have, as I said, when we have these linear predictors, then it boils down to least square problem. So we have arg min w. We are supposed to minimize this ls h w, which is arg min 1 by m w xi minus yi whole squared. So this is when our h is of the form w transpose x, then essentially we are trying to do this. We are trying to minimize w transpose x minus yi. As I said, we can use a gradient descent method to solve this. So if we compute the gradient of this, then the gradient will be gradient with respect to w, right? So gradient, if we want to use gradient descent, the gradient of this with respect to w will be 2 by m sum of w xi minus yi, and then xi equals to 0. So we are looking for a minimizer of this. So since we are looking for a minimizer of this, we took the gradient and equated it to 0. So we took the gradient with respect to w. So after computing gradient, you can check that this is the gradient of the above objective function with respect to w, and we equated it to 0, and then from here we can rewrite these as a, which is xi transpose I equal 1 to m, and b we can rewrite this as yi xi I equal 1 to m. Okay, so you can check that the a will be after some algebra, a can be written like this, and x will be the w here. Okay, so then we can write this as the linear system ax equals to b. Okay, where x is w. So the another way, from there I will relate this. So let's say I have wixi, right? So the way it is like this. So in terms of matrix and vector, it's very clear. Okay, so these are my wi, and the xi's are like this. So this is my x1. Okay, this is my x2. Okay, so let us do this way and then we will derive. And this is my xm. Okay, so this is how it is in terms of matrix. And what we want is these is y1, y2, ym. Okay, and we have built a loss function based on this. So basically what we have done is ax minus b norm of 1 by norm of ax minus in this case it's y, let us say. So let us say like this, aw, and since this is x, so let me use like this because then we will relate to this, minus y. Okay, this is what we are trying to minimize, and 1 by m you can take as well as a normalizing factor. So this is our loss, right? So for the current sample, I take a dot product with that and I check whether the output is y1 or not. Second sample, I take a dot product and then check whether the output is this or not. Okay, and here so if you now expand this as a 2 norm, you get exactly the loss that you have. Okay, so as I said, it's a vector x1 w1 y1, right? So this is x1 w1 transpose minus y1 squared plus x2 transpose w2 minus y2 squared plus dot dot dot. Okay, and then the last term. So that's what is written there, 1 over m. You are taking sum over, it's not w1, it's w is fixed. Okay, so x1 for the first sample, x1 transpose w1 minus y1 and so on. Okay, so this is in the matrix form. Okay, now if I take a derivative of this, okay, so essentially I would prefer to see loss like this. Okay, so this is our loss function w, and then if we take a derivative of this, right, with respect to w, okay, then we are led to an equation xw equals to y. Okay, so gradient of L with respect to w is 2 by m, which is very similar to that, 2 by m xw minus y is the gradient of this. Okay, and we want this gradient to vanish. For an optimal w, we want this gradient to vanish, so this gradient will be 0. And so this is exactly what you have here in the star. Okay, so now now to relate to that, what I will do is, since this could be rectangular, right, so I get rid of this, right? So what I have is this linear system xw minus y equals to 0. Okay, so x is this matrix and w minus y equals to 0. So that's, from this view everything is clear. I am up until here. This is the optimality I need for w. I need to solve for w basically, but the problem here is that x can be rectangular. Okay, so the linear system we are supposed to solve is that xw is y. Okay, so this is the same thing as xw is y, but then this could be rectangular. So what do? You will project it on a space where it becomes a square matrix basically. Okay, and then you can argue about, given that it's let's say full column rank, so A transpose A will be square with full rank, and then you can invert it. Okay, so what we have is that it could be rectangular, so we multiply by x transpose on both sides. So multiply by X transpose. So what we have is X transpose W, X transpose XW is equal to X transpose. And now I collect X transpose X as A, small x as W, and the right hand side is exactly X transpose Y. Okay, so this is A, this is the W itself, and this is the B that we are looking for. Okay, so usually the derivations we do are like this, but they are related. Eventually you can see both are same. So X transpose X is exactly the A that you are looking for. Okay, and then X transpose Y is the B that we are looking for, and W is the same W. Okay, so what is important to note is, like, I have to do some projection. Okay, because in general I cannot solve this. X can be rectangular, as I said. Okay, X remains rank deficient, then still there can be a problem. Okay, I am expecting X to be at least full rank, and full rank in the smallest possible dimension. Okay, so in this case it's I mean, if it's full rank in the column, let's say. Okay, the ranks are same, right? The row and column rank are same. So but then in this case the column size is smaller than the row, then A transpose X is Rn. Let us say this is M by N matrix. Okay, where M is larger than N, let's say, and X is full rank, meaning X rank is N, then X transpose X will be N by N. It will be a full rank. Full rank meaning non-singular, and hence inverse will exist. And if you are unlucky, even if it's not full rank, then you have to go for the various other cases where you can have infinitely many solutions, or you may have no solutions in those cases. So in those cases, you may have to go for some best possible approximation, in the sense of I mean, there may not exist a W for which this becomes 0. That's what we are trying to say, right? But there may exist a W for which this is a minimum, right? So the least square, what it tries to say is that just give me the minimum. Okay, the minimum will exist, as I said, when X transpose X is non-singular, and then it's invertible, and then all this is fine. Even in these cases where it has full rank, it's when X is square, then we are saying that okay, what we get is a unique solution here. But the fact that X is already rectangular, you are already looking for least square solution here. Okay, so least square means that it is not necessarily going to be 0, but it's going to give you something minimum is possible. So this is called normal equation approach, where I multiply by X transpose, I project on X transpose and make it a square, and then use linear algebra to solve this. But there are many other cases where we can, I mean, to solve such problems, I have like QR method and SVD. Okay, so there are like different type of methods to solve this, but that's a linear algebra thing. We have derived star, and it was convenient for us to use matrices, and we arrive at the same thing. This gives you a better picture because you understand that a projection step was needed, X transpose X, on which I could solve the problem. Okay, so that gives you a better picture of least square problem. So if it happens that A is invertible, then it's a one-step solution. If it's not, then you may look for pseudo inverse. Okay, so let me like give you one idea of what happens if A is not invertible. Then you work with something called pseudo inverse. So if A is invertible, okay, so let us use this way. Okay, if A is invertible, then we have unique solution. We have unique solution of this. Okay. So, but if not, okay, then we go to some linear algebra tricks. Like, for instance, I will define something called SVD, or in fact, I can define pseudo inverse based on eigenvalue also. Okay. So now here there could be two cases: A is symmetric, A is non-symmetric. If A is symmetric, then it has, we can talk about some eigenvalue decomposition here. Okay. So then, based on the eigenvalue decomposition, because it's singular, then there will be some zero eigenvalues. So we have to handle those zero eigenvalues separately. Okay, that's the trick of pseudo inverse. Other you can invert, but zero ones you just don't do anything. Okay, so let me specify that. So if A is symmetric or Hermitian, right? Then and in fact, it's guaranteed that eigenvalues will be real, so it's a bit easier to define in the symmetric case. Okay, so then so yeah, if A is symmetric, then eigenvalue decomposition exists. So then this is V D V transpose, where D is diagonal with eigenvalues on diagonal. And V is the eigenvector. Okay, the columns are eigenvectors. Okay, so this is the eigenvalue decomposition, which could also be written as AV is VD. Now, if you AV is VD. Okay, so and if you restrict to column by column, then it's like AV is lambda V. Okay, so if you want to see a column by column picture of this, so matrix multiplication, I can see this as multiplying one column here and the first column here, then it's exactly V2 Vn, and D is the diagonal matrix lambda 1 lambda 2 lambda n, and here it's A, and then V1 V2 Vn. So this is what we have. So A times the first column V1 is lambda 1 V1, A times second column is lambda 2 V2, and so on. Okay, so this is a compact way to write in terms the eigenvalue decomposition. So we can have an eigenvalue decomposition in this case if I mean, we can have it if it's asymmetric. Okay, that's the guarantee, and with the guarantee that also these are V are orthogonal also. So let us define pseudo inverse. So as I said, if A is symmetric but still singular, then certainly there will be some zero eigenvalues. So so it's not invertible in the direct sense. So this means that the goal is to use eigenvalue decomposition, but then D will have some zero eigenvalues. So if I am writing inverse here, and V are orthogonal, so inverse of V transpose is V itself. So that is fine, inverting, but then how the whole inverse will be V D inverse V transpose. Yeah, I think so. So the inverse of this will be V D inverse V transpose. So V D inverse V transpose, V transpose gets away, and D inverse will get cancelled, V transpose will become identity. So V D inverse V transpose is the inverse of that, right? Now the problem is, so V D inverse V transpose is the inverse of, is that correct? Okay, so is V D V transpose, right? So you multiply V transpose identity D inverse is, but the problem is, like, if A is singular, then then D has 0 eigenvalue. So this can't be taken as an inverse straight away. Okay. So if A is singular, then D has some 0 entries on diagonal. Okay. So if G has 0 entries on the diagonal, then certainly we can't take this as inverse. So what will you do, right? In that case, the pseudo inverse is when you don't touch the 0 ones, only invert the non-zero ones, and define that as a. So what is the notation? A dagger, right? So let us define the notation A dagger is usual notation for pseudo inverse, and D inverse also they use dagger. Okay. So V D dagger V transpose. So now we have to define what is dagger, right? So D dagger is let us define it point wise, right? Okay, let us define it because this is a diagonal matrix. So D dagger I is 0 if D I the diagonal ith diagonal entry is 0, then you don't do anything, you leave it 0, and this is the inverse. It is D inverse. Okay. IA otherwise if okay, otherwise may be confusing. DII is not equal to 0. Okay. So we have defined a pseudo inverse. Okay. There can be different ways to define pseudo inverse. Okay. Pseudo inverse may not be a unique thing. Okay. But this is one possibility I can define, and then I treat this as an inverse. Okay. I treat this as an inverse and then I solve the problem with this. So our original problem was the least square problem, where we had to solve AW equals to B, right? Now let us say A was symmetric but not invertible. So what I was looking for to solve this, it was ideally I was looking for A inverse B, but A inverse doesn't exist. So I will say that let us do it with A dagger B, where A dagger is the pseudo inverse of A inverse. So A dagger is I think we should use A pseudo inverse of the matrix A. Look, pseudo inverse is generic, right? So if it so happens that A was invertible, pseudo inverse will be the inverse itself, because it will never go to this case, because none of the diagonal entry were 0, because if A was invertible, then pseudo inverse becomes the inverse, actual inverse, where D dagger will be D inverse. So we have written a very generic way. If not invertible, then you will do this. It's invertible, then this becomes the actual inverse. So anyway, we have now a generic solution for all the cases. Look, this is symmetric anyway. Okay. So I've told you that if A is symmetric, it is symmetric because it is of the form A transpose A. Any matrix of the form A transpose A is always symmetric. So symmetry is guaranteed. So in general, we have a generic solution for the least square problem. Okay, with this combined. So what we did so far, we solved a linear regression problem. So basically, given this set of data points, we know how to fit using a plane. Okay, so linear functions basically, and obviously machine learning goes into much advanced topics where you want to fit very arbitrary class of functions, non-linear obviously. So as I said, since beginning also I have been telling you about fitting. So we have already discussed that there are possibilities to use polynomial as well. So polynomial also fits directly here itself. Okay, in this, in fact, polynomial fits directly in the least square sense also, because in place of x, what I'm saying is now I have x, x square, x cube, and so on. Okay, so in that sense, it's also very nicely fits into least square problem. So let us just write down few lines about the polynomial regression as well. So this is 9.2.2, okay, polynomial regression, polynomial So in polynomial regression, we are rather than using lines, now we are allowed to use polynomials. So in this case, we choose polynomials which are a naught plus a1x plus a2x square plus dot 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 plus an xn. Okay. So as you can see, the difference here is that in place of w1, w2, and so on, the components, now we have a naught, a1, and so on. Okay. So this can be written in the form as this a phi x. Yeah. So the way we have to see this is, yeah. So just a little bit of correction. What I said is W's are like A, okay? W's are like A, and the features have been transformed a bit, okay? So now you're looking for A naught, A1, sorry, 1, X, X square, Xn, and so on, okay? So this could be seen like this, A times phi x, and then this again becomes a least square problem, okay? Because again, I prefer to use the matrix form. So in fact, I have done this already once before as well. So in this case, our features become 1x, x square, xn, and these are for the first sample. I have the first row, and then the second sample I have the second row, and so on. Okay, so this, and then this is multiplied with the A in this case, so which could be seen as W as well, and this is equal to the output that we have after we have these. So let us say those outputs are y1, y2, yn. So once again, it fits very well in the least square sense. From here onwards, everything is the same, because this, now you take your A to be this, okay, and you do the same tricks that you did before, okay. So this is your AW equals to y, and again A may be rectangular and so on. So you know how to go ahead with solving this, okay. You can multiply by A transpose and use the same technique. So least square problems can be solved via linear algebra techniques. And as you can see here, when we say linear algebra technique, we never used gradient descent, because these are like direct methods, okay. So by direct method, we mean that we have to compute some eigenvalue decomposition, which we believe that it happens in one step. At least when we write in the MATLAB or whatever, it seems to exist in one step, but then if you go into numerical linear algebra, then eigenvalue decomposition itself, actually it's an iterative process, but we kind of think of those as a direct process, okay. So basically you do some kind of QR decomposition to build eigenvalue decompositions, okay. There are many variants of numerically obtaining eigenvalues and eigenvector, but still they will be called direct methods, because factoring a matrix Gaussian elimination LU, or factoring a matrix as QR, factoring a matrix as eigenvalue decomposition, or many other, actually the whole set of matrix decompositions exist. So these are called, yeah, I mean, using these methods to solve a problem will be called a direct method, okay. Although I know very well that computing QR needs a lot of iterative approach, where you build some projection steps, Householder projections, and then but then for our case it's like, at least it's not gradient descent, it's just call some eigenvalue decomposition and then solve your problem. So okay, so so what we have seen so far is we have seen a classification problem with a linear predictor. So this we did in the last class, and we used a sign, and then we built a loss function, and we used gradient descent, and so on. Okay, we can also pose this as a linear programming problem we have seen in the last class. So so it could be posed as a linear programming problem, it could be posed as a perceptron problem. Okay, so all this we have seen in the last class. We have proved the guarantee of convergence. Then we went to regression problem today, and in regression problem we are fitting the line. Again, it's all line because it's linear, but then essentially you can also talk about polynomial because it is like a least square problem again, because although these guys look nonlinear because of the power and so on, but then because this is a given data, this takes a value, right? So this is no longer a variable, so this becomes constant. So overall this becomes a matrix itself. So this is again in the framework of linear least square problem. Okay, so overall we can actually also fit a polynomial via least square framework. So all this is part of this. Now if you go to 9.3, which is a logistic regression. So so what we have done here, if you can see, is linear approach. Logistic regression is a non-linear approach to classify data. Okay, so meaning that it will allow some for classification only. Okay, so it will allow something like this. Okay, so that's in the 9th chapter. This is the last part of the 9th chapter. So let us study logistic regression, which will use, rather than the planes, because this is also kind of a equation of a plane. So rather than looking for planes, can you look for some other kind of functions, okay, which are not necessarily planes. So that's the logistic regression. So this is 9.3 logistic. So this is used for classification task. Okay, so there will be a little bit of confusion. Okay, in the literature, even people in machine learning, they recognize this problem with the naming. So they call logistic regression, but it's never about fitting. Okay, so you should be a little bit careful. Logistic regression is about classification. Okay, but when someone says just regression, then actually regression means just fitting data. Okay, so you should not get confused usually. Okay, this is a confusion point usually happens. So when people say regression, then they talk about fitting data point, and when they call it logistic regression, then it's actually classification, not data fitting. Okay, so let us see. So this is used for classification. Okay, for classification. Okay, so in this case, as I said, so far we were using equation of a plane, W transpose X form, right? Or W transpose phi X. That's what polynomial did, right? So still in the framework of plane, right? At least the model looks like that. But here, what will be that? So here it's not the plane. Here, the functions that we used are something called sigmoid. Okay, so sigmoid, which is defined like this. Sigmoid will also play a very important role in neural networks later on, because it is used as an activation function later on. So if we plot the sigmoid function, then it looks like some S-shaped. Okay, so it is kind of like crosses the half. Okay, I mean, a mistake here. It is exponential, right? So it will never be below 0, right? So it crosses the half and then it flattens like this. It's kind of symmetric around half. Okay, so this is sigmoid. So this is a slightly different type of function we are looking for, which based on its marker, which is half, which is where it's trying to kind of cut from the negative to the positive. Okay, so it's not a clear-cut classifier, as we will see, like the sine function of the W transpose X that we used. So sine will clearly tell you that it's positive, you go there, negatives go there. Here, we are not using any sign, right? So here it might tell you with kind of certain probability that okay, you are 90% probability that you are +1, okay, 10% probability that you are -1. So there is this flexibility here because we never use a sign exactly. Okay, so we will see that what I'm trying to say. So let us build on this. In this case, our hypothesis class, because we are looking into this kind of function, so our hypothesis class is like this. So let us define this class as phi sigmoid, and it is applied on D because the z that you have inside the exponential, it's W transpose X. Okay, so that's why I see this as composition of LD, which was the equation of the hypothesis class for the planes. So this is phi sig and then W X and W in RD, right? So so in place of z, right, you put W X, so it will be minus W transpose X here. So that's why we have sigmoid composed with LD, because in LD we have LD is W transpose X. So what you're saying is that first do W transpose X, and then you take sigmoid of W transpose X. Okay. So then, so a natural question now is when W transpose X is large, what can you say about the phi of W transpose X, right? So let us look into cases, right? So W transpose X is very large, let us say, very large. Then phi sigmoid of Wx is where, right? So if W transpose X, so basically I'm saying that if the argument Z is very large, what will happen? Phi sigmoid will go where? 1, right? So you agree? If Z is large, this will go to this one, 0. Okay, so this will go to 1, right? So this goes to 1, right? And if phi x is very small, so if I mean the z, right? So if Wx is very small, then it goes where? It goes to z goes to infinity, then exponential of x goes to by Wx we mean not necessarily close to 0, I mean even negative, let's say negative. So z goes to negative, then like very negative. It is allowed to go to infinity, right? Then this goes to 0, exactly. So this will go to 0. Okay. So I was saying 0, but actually it's allowed to go to even negative infinity, let's say. So then in that case, obviously this becomes infinity and overall thing goes to 0. So this is what the graph is also telling us. So if we look into the linear predictor, right? So linear predictor, we were looking into the sine and the angle and so on, right? So if sine is positive, then obviously it's like, if it's more positive, it's good, right? So in this case, what sigmoid is telling you is a little bit more, okay? So more positive, which means like more on this side, okay? Less positive means more on this side and so on. So the cutoff seems to be half, okay? So so compared to sine, it's here it's telling you it can tell you about how much more to the one class and how much more it's towards the other class. Okay, so that's the basic difference here in sigmoid. If W transpose X is close to 0, then it's like exactly at half. Okay, so if the z is 0, then it is half. Okay, then it's essentially confused. Okay, it's not able to tell you where the sample could be in the positive or the negative class. So the predictions of half space. The half space is the one that we did in the so far. Okay, the linear predictors. Okay, so we also call this half space hypothesis because there is a hyperplane, and on the one half space we have one class, and another half space we have another class. Okay, so the prediction of half space hypothesis is similar to, are very similar whenever the mod of wx is large. So whether it's very negative or very positive, the prediction of both of them will be similar, because sigmoid will also, because if it's very positive, then it's somewhere here, let us say, so it's touching 1 anyway, so it is predicting that it's class 1. Okay, and if it's very negative, then it will tell us that it's the other class, which is the 0 class. Okay, so in those cases it will clearly tell you which class the sample may be. Okay, so but in cases where the mod of w transpose x is not very large, which could be cases which is somewhere here, so then it will be somewhere here, these values it will predict. Okay, which is a little bit confusing. Okay, although it can now it's up to you actually. Okay, to tell whether, now it's up to you to tell, okay, whether you are okay to tell that this is in the negative class or this is in the positive class. Obviously you have to make a decision anyway, but in the sigmoid case it's giving you these things where you can tell how far it is from the other class. Okay, so in some sense you can say that it's giving you some kind of a probability, because it values between 0 and 1. So if this class is somewhere here close to half, then you can say that I feel that there is a 50% probability that this data point belongs to class 1, because it's just above half. Similarly, you can say that for this data point, the sigmoid is giving me the value close to half, so I am saying that there is a 50, or let us say it's slightly less than half, so we can say that there is a let us say a 45% probability that or there is a 55% probability that it's on this class, or so that way you can see that it's you can see this as a probability values basically. Okay, so let us given that we have this sigmoid model, and as usual now we will build a loss function that we will train, and we will train this sigmoid to learn to classify. Okay, so next step is to build a loss function basically. So next we need to specify a loss function. Okay, so in other words, loss function role in machine learning is to tell you, guide you basically, right, about how far how much error you are making on the supervised data. So so clearly what we have from our intuition so far is that we want this sigmoid value to be large if the data point is on if the data point is, let's say, one class, positive class. In this case, let us say positive class is this side, negative class is this side. So this is some intuition we have, is that the loss function should behave in a way that if it's on positive class, it makes very large, gives me large value. If it's a negative class, it gives me very small values. So that is what we need to quantify here. So clearly we want HWX is large if y is 1, let us say, meaning this class, let us say, is 1, and that okay, we are taking 1 minus, okay, so and that 1 minus HWX would be large if y is, let us say, minus 1 class. Okay, the usual notation for us for positive class is +1 and negative class is -1. So we have taken a negation of SW. We are doing 1 minus SW. So we are saying that if it's another class, then the 1 minus of SW should be very high. Okay. So from this idea, what we believe is that a loss function would be such that it would increase with, so a reasonable loss function would increase monotonically with 1 divided by 1 plus expectation of y w transpose x. You see, I have included a y there. Okay, it's a similar trick that we did for linear predictor in the previous class. So in w transpose x, it's like positive or negative, it's taken care of by y. Okay, so if it's w transpose x is positive, y is +1. If w transpose is negative, then y is -1. Okay, so what we want is that this should increase, okay, monotonically if w transpose x increases, okay, or in this case, let's say the mod of the w transpose x increases, right? So our equivalent statement would be, we take this a negative as well and move it on the numerator. Equivalently we say that 1 plus exponential of minus y wx. So whether I say that it's increases monotonically with 1 by 1 plus exponential y w transpose x is the same thing as saying that 1 plus exponential of minus y w x increases. That's because I took the negation here. So if this is supposed to increase, then exponential of minus y is supposed to increase. Okay, so that's another way to kind of characterize this. So with this, and what I can do additionally is that I will apply a log, because log is a monotonic function. So composition of a log with an increasing function will keep the increasing behavior intact. Okay, so log will be applied as a next step. So in logistic loss function, that's what they will do. They will use the log on this. So the logistic regression penalizes HW based on the log of 1 plus exp minus y w transpose x. Recall that log is as I said, log is an increasing function, so the behavior remains intact, which is what we are supposed to do. So note that log is monotonically increasing. So with this, we make a final loss function which will be log of 1 plus exp of minus y w transpose x. So that will be our loss function, which we write as small l hw xy and this is log of 1 plus exponential of minus y w transpose x. So this is the main thing about logistic regression. This is the final thing. Basically, you build a loss. Now it's all about gradient descent. You minimize this loss with respect to w. X and y are given data, so those are unknown. Those are known for you. The only thing is w. With the w, you will try to minimize this. And this loss is calculated for 1x, and we can make this a loss as a sum of losses over all the x. Okay, so then we can have a generic for sample for the training sample S, which is the pair x1 y1 dot 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 xm ym. We can build a generic loss function which will be so the overall training will be like argmin of the sum of these losses. The reason why the log, log will not change the minima. That's the thing. Okay, so so if the minima is achieved for certain w, then the same w minima will be achieved for log of that function. Okay, so these are equivalent optimization problem. So basically we solve this now, argmin over w, and then 1 by m sum of log of 1 plus exp of minus yi w xi. Yeah, so this is I equals to 1 to m. There is a mistake I have done. I want to clarify. It's not that, so we are looking for a loss function, and then the correct way to say is that the loss function should be monotonic with this. Okay, not like increases directly. Okay, so what we are looking for is, so let me so equivalency, we look for loss function that increases monotonically. There is a difference between that. Okay, I hope you understand this. So let me tell you from the optimization perspective. Okay, so it's not that the function itself has to increase always. Okay, so let us say I want to build a minimizer for this. Okay, so obviously this is not monotonically increasing or decreasing throughout, but what we are looking for is that when we build a loss function, let us say based on this, then what I want is that the places where the minima is achieved for this loss function doesn't get destroyed in the process. So in this case, we were looking for this guy. Okay, 1 plus, which is not necessarily the plot of this. Okay, in fact that may be convex. Okay, so that may not be like this, but anyway, let us say this is some function. Okay, so in that case, let us say this is some fx. Okay, generic way, and then I am looking for a transform G such that the characterization of the minima of this doesn't get changed. Now what could be that? So usually we do this in optimization. So what we do that is I will apply a monotonic increasing function on this. So for instance log. So if I do a log, then it might kind of decrease the minimum. So if I do it right here, right? So if I apply the log, it might do like this. So the places where the minima was achieved for the f didn't get changed because of the fact that the log of f that I applied, log was monotonic. Okay, you can prove these facts. If you apply a monotonic function on a function given f, then your minima or maxima won't change. That's how we get equivalent optimization problem. Okay, so here the correction I want to make is this function may not be monotonically increasing or decreasing, but I'm looking to build a loss function based on this, and if I have to do any transformation on this, then I will apply some monotonic function like that. So in this case, it's log is applied on that. That's what logistic regression does. Okay, that's the feature of logistic regression, that you apply a log transform on that, and the argmin doesn't change. Okay, so what we are trying to say is that argmin of this guy is same as the argmin of log of this guy, and these things you can find in Boyd chapter on convex optimization, convex functions, I think. Yeah, convex functions, or it was, the chapter name was convex optimization problems. Okay, I'm not sure exactly. Convex optimization problems, I think. So this is discussed in detail, like when you are given a set of functions, then when you can say that certain transform will not change the place. It does change the minima, I'm saying, okay, but it's not changing the place where the minima was achieved. So let us say your original minima was for this function was x star, then the minima of the log of that function is also x star. So that's why argmin remains consistent. So that's what is done here. Okay, so when we say that it's increases, then we say that if the function is increasing, log is increasing. Okay, so that's what it says. We are looking for a loss function that increase monotonically if this increases. If this increases, then the log of this increases. If this decreases, then the log of this decreases. Okay, that's what it means. Okay, it's not saying that it increases all the time or it decreases all the time. So that's a justification here, that this is our logistic loss function here, and we are supposed to minimize this. Okay, so that's basically now an optimization problem, and furthermore we can check. So now the fact that this is an optimization problem, now we can verify whether what type of optimization problem it is, right? So now it becomes optimization problem. So then you can say, is this differentiable? Is this convex? Is it strongly convex? Does it satisfy some basis continuity? So from here onwards, it's optimization, right? So you can verify that this is convex in W. Okay, so you may check this, because it could be double derivative test you can apply, because it seems to be invertible, right? So check whether this is convex, because if it's convex, you know, right, the convergence guarantee is there. Okay, check whether this is convex. You can use double derivative test. There is a sum there, but it's fine. Individually, if they are convex, okay, it should be fine. Okay, so okay, what else? So basically that's the thing about linear predictor chapter. So we are done with this. These are kind of preliminary things. When people use machine learning these days, they don't do logistic stuff that much. I mean, for a background, these are good things, but now everyone is doing deep learning. But these are basic things that one has to kind of like recall before going into something more complicated like neural net, because sigmoid is used as a activation function in the neural network at some point. So we will see that. So any question for today, from today's class, like anything, any specific question that you have in mind? I don't know what time. It's 12:40. Okay. Because I'm done with this chapter, so I'm thinking, should I start new one? So I'm thinking, should I start new one, or should I do it next time? Yeah, let us do next time, because it will become a khichdi then. Yeah, let's do next time. So think about this, logistic regression. Try to solve problems from the book. Then you will see if you really understand things.